Hello. Is that too loud? Is that all right? All right, good morning, everybody. That sound okay? All right, so let's do a little bit of fun with load and store and endianness. So we're going to do that today, and we're also going to look at more programming. I fixed the typos in the slide deck from Monday, and it's also loaded under the ARM programming module, and I added to it. So it was uploaded yesterday, so if you got it yesterday. Anyway, but let's try this just for fun, because, you know, yay. Oop, can you see that? That's pretty small, isn't it? Whoops. You know, it might be a little small to see, huh? You can't even see the answers. Oh, well. Yeah. Whoops. So this one won't work because you can't even see the answers. I think I'll skip this because you can't see it. Yeah, I'll redo this because you can't even see what the answers are. All right, never mind. It was worth a try, but we'll do more of that. I don't know. Maybe I'll just go through it by hand. Okay, let's go back to here. Maybe next week when I'm reviewing for the examlet, I'll try doing that again, but in a font that perhaps you could read. All right, so we did all this. Is there any questions on the endianness? Okay. So we went through this. All right, so this is where, so this is in one of the videos, but so when we do a set flags, there are 4 flags in the ARM programming language. This flag N, Z, V, and C. So N is if the result is a negative number. So you can actually use this in an add S, and both of them say, is what's in the result a negative number? If it is, it gets set to 1. So when you do a subtract and set flags, if this thing is negative, that bit gets set to 1. If the result is 0, so if x21 is 0, Z gets set to 1. I love that. If it's 0, it's 1. If it's not 0, it's 0. Anyway, if there's overflow, so we'll talk about overflow when we talk about numbers in a few weeks, but if the result is bigger than what will fit in the number of bits we have, so if it's a 64-bit number, it's, you know, the number won't fit in 2 to the 64th bit. It's, you know, it's bigger than 2 to the 64 or so on, or 2 to the 32 if it's signed. The overflow bit gets set. Carry out is actually the same thing. So we'll talk about signed numbers. So a signed number uses 1 bit for the sign. So the most significant bit is the sign bit. So if it's a 1, if you have a 32-bit number, the most significant bit, let's say it's an 8-bit number, just so I can write it, right? 1, 2, 3, 4, 5, 6, 7. And an 8-bit number, the most significant bit is used for the sign. So if that is a 1, that means it's a negative number. So in overflow is for a signed number. And overflow gets indicated when the sign bit changes. That means you have overflow. Carry out is for an unsigned number where all the bits are used just to say the number, so you can really only have positive numbers in unsigned. That just means a carry out, it's unsigned overflow is carry out. But then let's look at, so if you do a subtract and set flags, it's going to set these bits. And then you can do something called like a BEQ. It's going to look at the flags. And what it's going to say is, okay, if this 0 flag is set, that means this result is 0. That means x17 equals x19. Okay. Not equal. So then you can do a B not equal. Would mean x17 is not equal to x19. And then B less than. So what this says is x17 less than x19? And what it does is, if it's a negative number, and there hasn't been overflow, so let's say x17 is 10 and x19 is 17. 10 minus 17 equals -7. So that's a negative number and there hasn't been overflow. Or it could be it's a positive number and there was overflow. So if there was overflow, the most significant bit will turn to 0. We'll get more into that later. But it'll also, the less than flag will also get set if it's a positive number and overflow. And greater than is if it's not a negative number and there's not overflow. So the intuitive case is without overflow. So if it's not negative, then x17 is greater than x19. Okay, so that's how the flags work. And then you can use this branch if greater than. Okay, so you would do well, we'll just see how this looks, right? So what you do is you use the B dot whatever, and then jump to a label. Okay, so this is the code for this. This is the code for this. This is the ARM code that goes with this C code, right? So we're going to put the number 14 in register 14. We're going to subtract and set flag. So this is going to compare X, which is in X9, to 14. If X9 is greater than 14, we're going to jump to else, where we're going to set Y to 2 here. If not, we're going to do this line where we set Y to 1 and then jump to the exit because we don't want to execute the else. Good? Awesome. Okay, so here's a loop. I've sort of slowed down. You know, I think my second example was maybe a little much on Monday. So here's just a plain old loop. So we have X in register 9 and N in register 10. So somewhere else you would have set that up. So we're going to set X to 1 and then go for I equals 2 to N. Add X to itself. So I guess we're doing, the result is going to be X times N, right? All right, so yeah, there are multiplication instructions, but actually the result, well, so we'll talk about multiplication in a couple of weeks as well, but the result of multiplication is actually twice as big as, so if you multiply two 32-bit numbers, the result can be 64 bits. So we'll look at that. And so multiplication is a bit complicated because unless you know that your numbers are, you know, only 16 bits or whatever, it gets put into 2 registers, the result. But anyway, so we're not going to do multiplication yet in our code. But anyway, so let's first set X to 1. Set I equal to 2. Subtract and set flag. So we'll say, what is I greater than N, right? So that's what this is asking. Is I greater than N? If it is, jump out of here. If it isn't, add X to itself and add 1 to I. So I remember to do it that time. Yay. Okay, good. Go ahead. It wouldn't be correct. A logical shift left would just multiply by, well, I guess you're right. You could do that. Multiply by 2, yes. And I would think, yeah, it would be cheaper to just do the LSL. Right. So the person asked, couldn't we just do a logical shift left? Yes, we could. All right, another question, and then I'll answer what's on here. Go ahead. What is what? B? Branch. That's branch on greater than. So that's what I did. I was doing up here. So, yeah. Yeah, I kind of play fast and loose with capitals. Maybe that threw you off. But yeah, so the command is branch on greater than. So did that answer your question? Okay. So the XZR is actually register 31. So some of the registers, so register 31 always has 0 in it. I think probably if you felt like you could probably put something else in there if you wanted, but I think the tradition is that register 31 always has 0 in it, and you can, or X31 always has 0 in it, you can call it XZR. So that says the register with 0 in it. It refers to register 31. There's a couple of, so we'll talk about next week, we'll talk about the stack pointer and the frame pointer. So there's some registers where you could call it. So I don't remember what's what. I think the stack pointer is X30. Don't remember. But you can also in your code just call it SP, stack pointer. So it lets you call some registers with other names. So that's what XZR is. It's something that's just always 0. It's kind of a convenient thing to have around. And then what sub S is doing is saying subtract and set flags. So it's a regular subtract, and it's also setting these flags. So there's a number of S you can do. add and set flags, and in set flags. I don't remember all the ones. To me, the only one that's truly intuitive is the subtract, right? Because these greater than is actually saying, so subtract and set flags, then I do branch on equal, are x17 and x19 equal? Is x17 greater than x19? You can do add and set flags, and what it does is it looks at the result, and then if the 0 flag is set, it'll branch on equal. But to me, that's just not intuitive, right? So anyway, so I got all the questions. Good. Yeah, so what sub S is doing is actually doing the subtraction, and you have this thing in x21, but we don't really do anything with it. Okay. Yeah, when we start programming, we'll end up with all sorts of shortcuts that you'll learn are there, like XZR means x31. Okay. All right, so here's the one. I'm going to do this one again with no typos this time. So let's look at this loop where what we're going to do is go from 1 to n and check these two array, the array at index, the item at index I in each of these array, and whichever one is the smaller, we're going to put in C. So what we have is we have n in x9. The base address for A is in x10. The base address for B is in x11, and the base address in C is in x12. So again, what we're saying, so this is harken back to the, times of when people used arrays, probably more than you do now. But an array is all together in memory, and it has a base address, and you can move along the array by just adding to the base address, right? So if I want item 0, I just go to the base address. If I want item 1, I go, so we're saying that each address is going to be 8 bytes. Maybe because in ARM, it's a 64-bit language, so integers are going to take up 64 bits. Floating points are going to take up 64 bits. If you have a 32-bit language, maybe this would be 4 bytes, but we're doing 8. So if we go to the address plus 8, we're going to get a 1. If we go to the address plus 16, we're going to get a 2. Okay? All right. So first I'll write my loop stuff. So I'm going to put I in x13. I am going to check to see. So I'm going to do n minus I. And if it is 0, that means n equals I. So I'm going to go to the exit. So this is just the loop part. Okay. Guys. Now I'm setting up all the darn values. So this x15 is always going to have I times 8. So that's going to be the address offset for each item in each array that I want. Okay. So now I'm going to say, okay, the location of AI is going to be the base address of A plus I times 8. So x16 is going to have the location of the item in A that I'm interested in. Okay. And X17 will contain the value that's there. Okay? So X16 is the address where it is, and X17 is actually the value of AI. And then the same with B. So X18 will contain the location that I want of BI, and X19 will contain the value. And then X20 will contain the location of CI. Now, oops. A repeat. So now I have all of these locations. So now I did subtract and set flags. So I'm going to look at X17 and X19 and see which one is bigger. Is AI, so this is saying, is AI greater than BI? If it is, go to else. If it's not, do this. So what we're going to do is store the value in X17 in X20. Right, so this is saying, okay, what's in 17 is AI. So this is saying CI equals AI. Then I'm adding 1 to I because I forgot to do that last time. And then this one is saying CI equals BI. And then jump around. The slides are there under, you go to the ARM programming module and it's under sample problems at the bottom. So, good. How to turn 5 lines of code into like an obtuse hunk of 20. All right, good. Okay. Now, I have a little bit more here. So more with arrays. Excuse me. All right, so now we have I equals X2 and J equals X3. And the base address of A and B are in X6 and X7. So this is kind of just slowing it down a little bit. So let's subtract, X9 is I minus J, multiply that by 8. Get the address of AI minus J. So it's going to be X9 plus the base address. Put that value in X11 and store it in B8. Good? And more of the same kind of stuff. But with 2 loops. Awesome. Okay. A, I, B, and J are in X1, 0, 1, 10, 11, and D has the base address of. Right. So here, let's make sure that I and J are actually 0. Let's check to see that, so we're going to have the I loop and the J loop. So the I loop is checking I. So this says, has I become A? If it has, we're jumping out of that loop. This is now looking at the J loop, checking to see if J equals B. So here's the J loop. And here's where we have our fun with arrays. So this one, we're going to add I and J together. Multiply J by 4. Multiply 4J times 8 to get the byte offset of 4J. Get its address, add it to the base address of 2. So this is the address of D for J. Put that value into, oops. Oh, take the value of I plus J and put it at that address. So this is saying D for J equals I plus J. Add 1 to the loop and go back up. That file, I can go find it, but I put it back in there yesterday, I think. Maybe it's Monday, I don't know, but it's in there. All right, good on this? Fun times? Can't write nested loops in ARM? Okay. Ooh, fun. Okay, so let's look at this. Let's take a function. Oh yeah, this is a lot more. So this is, yeah, this has the stack. Maybe we'll start looking at, so I'll start looking at the slides. Start going over the slides for the stack because we haven't started that yet. I haven't written the examlet yet, but could be. You'll definitely be writing code, so I know. Let's start looking at all right. You're right. I never, okay. Yeep. Awesome. I thought I'd put it there, but I guess not. All right, let's start looking at ARM procedures. All right, so because this is going to be a big part of what we do for the next couple weeks. So first, let's start looking at, so you should look at these videos certainly before the examlet. There's a couple of them there. There's like 4 videos on ARM procedures. So first, we already kind of talked about, how memory works. So your main memory in ARM, the main memory is 2 to the 47 bytes. Each byte has a 64-bit address. Okay, so for each address, you're going to have, these 64 bits to describe it, and then where that address is 8 bits or a byte. We kind of went over that a little bit with the load and store. The addresses in ARM main memory go from this, this 0 to this. So outside of this area is stuff used by the operating systems. Oh no, under this. So user programs and data have addresses in this range. And then ones under it are used by the operating system. But this is what's important to you, right? So all of our programs are going to go in these addresses. So like we talked about how our programs are stored in memory. So each instruction is going to have an address, and it's actually an address. So each instruction is 32 bits long. We learned that, right? So an instruction is going to have a byte address. It takes up 4 bytes, and they have to be aligned. So if something is at address 0, the next instruction is going to be at address 4, and the next instruction is going to be at address 8, and so on. And in ARM, instructions have to be aligned on the 4s, right? So, but that will be in this text segment. In this segment, it's called the static data. So that is static variables, global variables, things that are bound by the compiler. What goes on the heap is here. And that is any dynamic data that you allocated. So that would be anything you use the new operator for, or malloc, anything that goes into your reference-based data structures goes on the heap. So when you clean up your memory at the end of your, after you have a program and you delete all your pointers and stuff and clean up your memory, you're cleaning up heap space, right? So the stack is all of your local, so we're going to talk a lot about the stack in this class. It's all your local variables. So when you run a method, you're going to have local variables in there. Those will go on the stack. So if you've ever infinitely run a recursive procedure, you have overflowed the stack, because every time you call a new method, a new stack frame gets put on the stack. And if you make too many, it's going to run into the heap. So these two things grow together, and you could run out of this room. So we'll look at in depth at what's on the stack frame, but that's what's happening. And it annoys me that it's called a stack, but it grows downward. I guess it's a stack with magnets because it actually, when you put something on the stack, it's actually lower in memory. I don't know. I find that annoying. There's so many annoying things. I guess it just keeps us on our toes. So I talked about this for a minute. This is what, the text segment is for user programs. We learned, already that each instruction is 32 bits. So it's going to take up 4 bytes. Yeah, so we're going to learn on Friday we'll look more, Friday in your discussion more, we'll look more at how to put together an ARM program for compilation. But you have this section called where you put .text. You have .data and .text. .text is where you say, okay, here's all my instructions. So it's going to go into the text segment of memory. We have a special register that you can't do anything with, so that's one. But there's something called the program counter, or PC. That's the address of the instruction currently being executed, right? So if you're not doing a branch, you're just going to add 4 to execute the next instruction. So unless you're doing a branch, or you're going to just do the next instruction and add 1 to PC. All right. So now, again, we already talked about this. What's in a stack frame? So a stack frame is a block of data that contains register contents and variable values, so that when you call a procedure, you don't lose the data. So when you, so you might have noticed when we looked at the registers, that's probably coming up like next. Yep. So these are all of our registers. Again, I said earlier, 31, register 31 is the 0 register, and you can call it XZR. You can also call it X31. So when you call so you're in a method, and you call another method, it goes and runs that thing and comes back to where it was, right? And you count on that happening. How it does that is by saving the return address. So what's in X30 is an address, and it's an address of an instruction that's going to say, what should I go execute when I'm done with this procedure? So that's what goes in the return address, and that's X30. The stack pointer is the top of the address of the top of the stack. So this stack, so it's wherever, what do I have on my stack and where is the top? So the stack can grow up and down, right? So where is the current top of the stack? That's this stack pointer. And then we'll also talk about the frame pointer. So every method has a frame. So there's a hunk of data associated with each method. So you know that you can run nested methods, right? So I call main, and then I call something from within main, and I call something from within that. There's something on the stack for every method I'm running. And so each method will have a stack frame. So the frame pointer is kind of telling you the bounds of where the information for that method is. Okay, these registers actually, X9 to X15 are called temporary registers. So they're not guaranteed to be saved. They're like local variables, right? So you're not, so in a method, it might be using X9 to X15. If another method is called, that method could overwrite X9 to X15 because they're local variables. So when you're running a method, you have some local variables, right? You go run another method, you come back from that method, you're going to assume your local variables are still there, right? But what actually happens is they get saved to the stack and then restored when you come back from the method. So it's like you never left, right? So what you have to do before you call a method is save all your temporary variables to the stack frame and then restore them when you get back. X19 to X27 are called save registers, and they're guaranteed to be preserved across a function call. So you don't have to save those to the stack. If this is kind of the only time you have to save X19 to X27 to the stack is if you're changing them in your method, or you need to use them, but the other method is assuming that they won't be changed, if that makes sense. Like, if you need to use them, like, you have to put them back as you found them. And then the other thing you'll see is x0 to x7. So when we have a method, we have arguments, right? So if you have two arguments in a method, you're going to put those arguments in x0 and x1. Okay. And then it also, the return value is going to be in x0 to x7. So these registers are used for arguments and results. Okay. So now when I call a method, so say I'm running something, some method, and I call another method from there. What I'm going to do is, so let's say I'm in main right now, so it's calling another one. What it's going to do is create a stack frame for the data it has to save. It's going to move the stack pointer. Well, first, it's going to set the frame pointer, so it's going to say, all right, my hunk of stack memory starts here at the frame pointer, and then I'll make room by moving the stack pointer. Okay, so it's saying this is how much room I need on the stack, right? So it moves the stack pointer that far. Okay. And it does its thing, you know, then it says, okay, I'm ready to call that method. I have everything I need saved. And then it calls procedure 1. So procedure 1 is running, and maybe procedure 1 is now in scope, and maybe it's calling another method, right? So then it needs to make its own stack frame. So then what it'll do is move the frame pointer and move the stack pointer. Okay, so that's kind of, you know, kind of how the stack grows is as we call nested methods. So as each one of these, you know, creates these stack frames, what it's saving is it needs to save arguments, right? Because they don't get saved, right? So it has to save anything that it's using from registers x0 to x7. It has to save the temporary registers, which is x9. I already forgot x9 to something. So, but any temporary variables it's using and any arguments, it has to save its return address because it might get overwritten. And it has to save its frame pointer. So it can, when it's done running, it can restore the stack and put it back. Good? Clear as a bell? You'll know stack frames forever now? Awesome. All right, so let's look at an example. So here, I'm running something called leaf example, right? So I have two arguments. I have three, G, H, and I, right? I have a stack pointer. So by the convention of ARM, G, H, and I are in 0, 1, and 2. Okay. And I'm going to assume that F is in X9 and J is in X10. Okay, so now the first thing I need to do, since there's a procedure call here, I have to save everything into a stack frame so it'll be there for me when I get back from that procedure call. Okay, so here, before I can call my procedure call, I am going to set up my stack frame. Okay, so the first thing I'm going to do is set up my frame pointer, right? So the stack frame for leaf example is going to start here and grow down this way. So its frame pointer is going to be where stack pointer is now, right? So here I'm resetting the frame pointer. So I'm saying, take what's in x28, which is the stack pointer, and put it in x29. Okay. So now I have my frame pointer set. Now what I'm going to do is create my space, right? So set up how much space do I need. So what I'm going to do is actually, all I have to do is subtract the amount of space I need from the stack pointer. This is saying, give me my space right here. Okay, so it's just moving the stack pointer. That's how I say how much space I need. And ARM has a rule that you can only increment the stack in multiples of 16. I'm not sure why, but I need space for 7 things. I need space for 1, 2, 3, 4, 5 variables. Plus I need to save the frame pointer, plus I need to save the return address. You always need to save your return address because it might get overwritten, right? If you don't save the return address, it won't know where it was supposed to return to. Right, so I need room for 7, but I make room for 8 because I can't do 7. You can't do odd numbers, right? So here I have created my stack frame. So I'm saying here is where I'm going to put all my stuff. Now I just go about putting the stuff on the stack. So the first thing I'm doing is putting x0 on the stack. So this is saying go to the address in memory that's x28 plus 48. So this is the stack pointer, and this is saying add 48 to the stack pointer and put x0 there. Okay. All right, so I got one thing on my stack now. I do x1 and the rest, right? So this is all the things I just put on my stack. Yay. Then I'm going to go ahead and run my procedure call. So what this is called is a branch and link. Okay. This is saying go to the line labeled my procedure call, but also that L says overwrite the return address, overwrite x30 with the address where I am right now plus 4. So this is saying after you're done running my procedure call, come back here. So branch and link will overwrite the return address. If you just do a branch, you better count on my procedure call somehow knowing where to send it back, but it won't. So anyway, so that's saying go to that thing, and then when it says, so my procedure call is going to say branch back to what's in x30, right? So branch and link is important because it overwrites x30. And that's why we had to save x30, right? So what's in x30 now will get overwritten, okay? And then I come back. So it's just like a regular, so now it's like, okay, the next thing is going to be coming back. So I just am going to go ahead and do this thing, but before I can do that, I have to restore all the registers. Okay, and it looks like I'm out of time. But anyway, this first thing, so this says J equals my procedure call. So G was X0, and the return is X1. So J was in X1, and we have to put it back in X11. So that's your introduction to stack frames. So I would suggest you, we'll spend some time on it, but it's important. Yeah.
You only have 8 registers for the temporary key method variables, right?
Yeah.